suppose we know that the acceleration of a particle along a space curve is given by, here's the acceleration vector, a of t equals 2, 6t, 12t squared. And the initial velocity and positions are known to be, this is the initial velocity, v of 0 is simply I, and the initial position, r of 0, is j minus k. What's the velocity and position vector that describes the motion of the particle along the space curve? Basically, we're going backwards. We just took a look at the idea of knowing the position function, and from the position function, I want to be able to find out what the acceleration and velocity vector functions are. Now this is saying I know the acceleration, and I know a couple of initial conditions, so I want to find out what the position vector is. Now recall that velocity is going to be equal to the integral of acceleration dt, which should make sense because remember we have this relationship. If we take our position vector, r prime is the same as velocity, r double prime is the same as v prime, which is the same as acceleration. So if I integrate v prime, I'll get v, but integrating v prime is the same as integrating the acceleration vector. So from acceleration, I take the integral, and from that, I can figure out what the velocity vector is. So this is going to be equal to the integral of, 2i, whoops, that's not a t, 2i plus 6tj plus 12t squared k dt, which is going to be 2ti plus, this is 6t squared over 2, so this would be 3t squared j plus, this is going to be 12t cubed over 3, so I'll have 4t cubed k. So, plus c. I need that constant of integration. Now, the kicker here is that I know that my initial velocity is simply I. So that means if I evaluate this when t equals 0, that's the 0 right there, that this, when I evaluate, must be equal to I. Well, when I evaluate for t equals 0, all these go away except for c. So that tells me that c is equal to I. Well, if c equals I, what I really have is the velocity vector equals 2ti plus 3t squared j plus 4t cubed k plus I. Well, obviously, I want to collect these like terms. So when I do, that's going to be 2t plus 1 I plus 3t squared j plus 4t cubed k. So that's my velocity vector. Now, it also asked for the actual position vector. Well, the position vector is going to be the integral of the velocity vector. And I guess we could, if you want to write this in this format, if you like this format better, that's fine. I didn't because I know I'm going to integrate this again, and I'd rather integrate in this form. So the position vector, r of t, is going to equal the integral of v of t dt, which obviously you can get from here, that relationship right there. So that's going to be the integral of 2t plus 1 I plus 3t squared j plus 4t cubed k dt. This is going to be, when I integrate this, it will be t squared over 2, so it's just t squared. The 1 is going to be a t I plus 3t cubed over 3, so this is just t cubed j plus this would be 4t to the fourth over 4, so that will be just t to the fourth k. Now I also know that at time 0 the initial position is j minus k. So if I evaluate this at t equals 0, this must be equal to j minus k. So at t equals 0, this is 0, this is 0. Oops. Hopefully you caught me. Plus c. I forgot my c. Now if I evaluate this at t equals 0, bingo. If I evaluate this at t equals 0, again, all these have t's in them, so I, j, and k go away. And I end up with saying, or getting c equals to j minus k. So that means when I collect all the terms, my position function, whoops, that's supposed to be a t, will be equal to, there's no i's here, so this is still, I'm going to write this like this now, t squared plus t. I have a t cubed j and a j, so this is going to be plus 1. Oh, don't need the parens because I'm writing it in this form. And then the k, I have t to the fourth k and a minus k, so this is going to be t to the fourth minus 1. So here is my position vector. And where did I write it? There it is. Here's the velocity vector. Given that we had this initial acceleration vector, and it's extremely important that we had these two initial conditions.